Okay, good afternoon, everybody. We are happy to have Dr. Yvan Six from Ecole Polytechnique for today. And today we will start to discuss about the organic synthesis as been requested by our divisions. For this year, we are focusing more on organic synthesis rather than natural products. So we are happy to hear that. At the same time, I'm a part of Organic and Biomolecular Divisions, Institute Kimia Malaysia. And for today, we will have Dr. Yvan Six, Deputy Director of Laboratoire de Synthese Organique from Ecole Polytechnique. And the title for today's sharing session is Haloaminocyclopropanes as a precursor of natural product like polycyclic compounds. Before we continue with Dr. Yvan Six, let me introduce him and read his CV. Okay, he started engineer degree from Ecole Polytechnique in 1993, and after that proceed with a PhD in organic chemistry at Ecole Polytechnique also. Under supervision is Prof. Lelemont with the title of Synthesis Approach Toward Clerodines and the preparation of high functionalized key intermediates. And after that, he proceeded with postdoctoral fellows in 1997 until 1999 with Professor Motherwell at University College London. He is a very famous organic synthesis in UK. And after that, in 1999, he proceeded also the second postdoctoral positions under Professor Samirzad in GIF Surivet. And after that, he created his own team in Institut de Chimie Substance Naturale in 2000s. And now he moved back to Ecole Polytechnique. And the current position is a deputy director. And he also established his own team and also have 30, more than 40 publications, including book chapters with H-index more than 70. Without further ado, now I invite Dr. Yvan Six, and I'm really happy to welcome you again to Malaysia, even though we are by using webinar. Okay, I give to you, Dr. Yvan Six. Okay, the floor is yours.
Thank you very much, Azmi. So thank you very much for the invitation. It's really a great pleasure for me to be able to speak in front of you. Of course, it would have been nicer to be there in Malaysia, especially now in November. It's raining all the time here. It's not very warm. So, well, maybe it's the rain season in Malaysia too. I don't know. Okay, so I will try and share my screen. Okay. And I'll have to start the presentation. Right. Can you see the presentation? Yep.
Yes.
Okay.
It's clear.
Okay, perfect. I'm not sure if I can get a laser pointer. Yeah. Okay. So before I start, and as usual, I will give you a very brief overview of the research activities of my team. So we began in the year 2000, so more than 20 years ago now. And our main areas of research are aminocyclopropane chemistry, then the synthesis of peroxides by aerobic oxidation, and we focus on antimalarial targets. This is also actually part of the aminocyclopropane chemistry. We've been working as well from the beginning on transmetallation reactions with titanium isopropoxide. And we are doing a bit of natural product total synthesis. This is in collaboration with my friend Azmi, actually. And today, I'm not sure. Oh, yeah. The talk will be on this part, on the aminocyclopropane chemistry part. So I will begin with some, let's say, presentation on our previous work on aminocyclopropanes, so what we've been doing from the beginning. This will be a rather brief part, and then I will focus on the aminocyclopropane part, and I will show you what we can do with that, like the synthesis of this kind of molecular structure. So why we are interested in cyclopropylamines or aminocyclopropanes? So one reason is the fact that several marketed drugs contain the aminocyclopropane moiety. Perhaps, I don't think I put it here, but there is also a natural product, aminocyclopropane carboxylic acid, which is a very important natural product that is present in every higher plant. It's a precursor of ethylene, which is a important plant hormone. And apart from that, so all of these drugs contain, you see the aminocyclopropane moiety. Another reason is that we can use aminocyclopropanes as precursors to generate reactive species like iminium ions or enamines or dystonic radicals or 1,3 dipoles, and this allows for the preparation of complex nitrogen-containing polycyclic compounds. So I will give you a few examples of that. First, a few words on the synthesis of aminocyclopropanes. There are several methods, but today probably the method of choice, which is the method we use, is the de Mayreux reaction or Kulinkovich-de Mayreux reaction. So this reaction, I think, was first reported in 1996 by the group of de Mayreux. It's based on the Kulinkovich reaction. So it associates titanium isopropoxide and a Grignard reagent. And in the most interesting version, this proceeds with the ligand exchange with an alkene. So the starting materials are a carboxylic amide, an alkene, and the product is an aminocyclopropane. The 3 carbon atoms of the cyclopropane are made of the carbonyl group and the 2 olefin carbon atoms of the alkene partner. So I will not bother you much with the mechanism. This is organometallic chemistry. What happens is first a reaction of the Grignard reagent, which is used in excess amounts with titanium isopropoxide. And this generates this kind of a funny organometallic species. It's a titanocyclopropane species. Then a ligand exchange takes place with the alkene partner to form another titanocyclopropane complex, and this one adds onto the carbonyl group of the amide. So this carbon atoms adds there. So you can view this as a carbonyl insertion into this metallocycle. This forms this oxo-titanocyclopentane intermediate. Then this carbon-oxygen bond breaks. So this is pushed by the lone pair of the nitrogen atom. This gives rise to an iminium species, which also still contains a carbon metal bond, and then there is a cyclization to form the aminocyclopropane. In my group, we work mostly on intramolecular reactions. So the amide and the alkene are part of the same molecule, and this gives bicyclic compounds with a quite important ring strain, which is good for the generation of reactive species. But the strain is not so large that the molecules are not stable, so they are perfectly stable. You can run chromatography of these compounds without problem. And with respect to the other, so of course we make a cyclopropane ring. With respect to the other ring, we can make 5-membered rings, 6-membered rings, 7-membered rings. There can be a chiral center on the starting material, and then there is a diastereoselectivity issue. So in general, diastereoselectivities are not very high, except if you have an aromatic ring directly attached to the nitrogen atom, in which case quite good diasterol selectivities can be obtained. So I should mention that the first example was reported by the group of Jin-Kun Cha in the US. So that was actually the synthesis of this molecule. And when we started, that was the only example, and we could demonstrate that the reaction is really quite general, in fact. So I mentioned some transformations we can perform. So one of them is protonation with a strong enough acid like a PTSA. We only need a catalytic amount of it, and we need to heat the reaction mixture to generate an iminium species. So we protonate at this position, get this iminium, and then an intramolecular Friedel-Crafts type reaction takes place, and we can make this kind of polycyclic compound. This is another example. In this one, we are generating an enamine intermediate. So we begin from this this salt. So the aminocyclopropane is protonated at nitrogen here, and we have a benzylic alcohol. We heat this with microwaves. We don't need to add any acid because the substrate itself is slightly acidic. And under these conditions, we protonate the cyclopropane here as before. So we first generate an iminium. Also, we protonate this alcohol, so it eliminates to form this alkene. And then this iminium loses a proton also to form this enamine. Then we have a fully conjugated system here, and an electrocyclic ring closure takes place, 8 electrons. So if you push the arrows, you will get to this intermediate. We still have a conjugated system with this atom, this one, this one, this one, and this one. And a 6-electron electrocyclization can then take place to form these funny cyclobutane products, which look like a little bit like azasteroids. We get a mixture of these two diastereoisomers in a 3:2 ratio in this case. This is another application. So again, we are heating with microwaves with a small amount of an acid. We protonate the cyclopropane again to generate this iminium. And this one is quite acidic. So you have hydrogen atoms here, which are quite acidic. And under the reaction conditions, they can lose a proton. So to generate an azomethanylate, which is a 1,3 dipole. We run the reaction in the presence of a dipolarophile. This is a ethyl maleate. And then 3+2 cycloaddition can take place. So this is the transition state. And we get this new product as a 1-to-1 mixture of 2 diastereoisomers. So all these stereogenic centers are fixed, and we have a mixture at this position. We also have a minor amount of this one. So you see the difference, it's here. So here we have a cis arrangement of the 2 esters. Here it's trans. And we could show that this results from partial isomerization of this maleate into ethyl fumarate. So in fact, at the stage of the cycloaddition itself, this is a concerted process, and there is retention here. But of course, if there is partial isomerization of this, it explains why we form this in minor amounts. Okay, so I will now tell you about the second part, which is a bigger part. And I decided to focus on that. It's our most recent work. So it's based on a classic reaction, which is an electrocyclic ring opening of cyclopropanes that are substituted with a leaving group. So if this is heated, a cyclopropane ring opening can take place. So this generates an allyl cation, and this proceeds with a simultaneous departure of the leaving group. So you get an allyl cation, and the counter anion is X- here. So this reaction was actually much studied experimentally with the group of Charles Dupuy. And there are some stereochemical aspects as well in these reactions that I will mention later. And these were studied by very famous chemists, Woodward and Hofmann, who could rationalize using a molecular orbital theory the observed outcome of these reactions. I will come back to it. So from there, the idea we wanted to investigate, because we like aminocyclopropanes. So the idea was what would happen if we have an aminocyclopropane substituted with a living group. So presumably the same type of reaction could take place. So this would generate an allyl cation, and this would be adjacent to the nitrogen atom. So we could expect stabilization of this allyl cation. So this is in fact an iminium ion, and a delocalized iminium ion, so very stabilized. So thermodynamically, these reactions should be very favorable, and we hoped. Oh, something happened. I'm not sure. Let me see. I have a strange window opened. I will just close it. Oh, I'm sorry. I have to restart. Yeah, I apologize. So I think I closed the presentation accidentally. I will reopen it. Okay, can you see my presentation again?
Yes, it's clear.
Okay. Yeah, sorry about this.
No, it's okay.
Okay, so I continue. So we were also, so as I said, the allyl cation that we are generating should be stabilized thermodynamically. And also in the process from here to here, we have a positive charge that is gradually developing. So we were also hoping that the transition state would also be stabilized by the nitrogen atom, and the reaction would be easier with the presence of this nitrogen substituent. And actually, in the literature, there were a few examples, very few, of this kind. So here, it's a cyclopropanation of an enamine. Of course, this is not a stable species. And they observed that at room temperature, there is a spontaneous ring opening. And so this is a kind of a proof of concept. So the reactions, it looks like it's much easier than in the traditional case where we have to heat up the reaction mixture. But this example arguably is not very, very interesting because the nitrogen part is lost at the end. There is just a hydrolysis of this. This is a much more interesting example where, in fact, this intermediate opens also spontaneously without heating, and the iminium is reduced with lithium aluminum hydride, and this gives a nice product. But in this work, the conditions were actually not detailed, and also making this starting material is really quite difficult. It's a multi-step synthesis, and also this is not very stable. This is readily used, actually. And then there was this example where this PROC-protected difluoro compound is deprotected. And they observed that in a chloroform, deuterated chloroform, this is not stable, but the half-life is reasonable. It's 2 days. So it gradually opens up to this, which was observed by NMR. And then this is hydrolyzed to this cyclic imine. And in the literature, you can find many more examples that involve not an amine, but an amide. And in this case, the ring opening is more difficult, so it's necessary to heat up again to obtain ring open products. And this makes sense because the lone pair of the nitrogen atom is delocalized with the carbonyl group. So you don't have this assistance that I mentioned before in the ring opening. And you can see that typically the yields are not very good, or the conditions are quite complicated with expensive catalysts like this palladium catalyst. Okay, so our strategy to explore this in more detail was to use a reductive elimination reaction. And we wanted to do this with this kind of salt. And we were hoping that in general, these salts can be stable. And indeed, there is no available lone pair on the nitrogen if we work with the salt. I have to get back to the laser pointer. Yeah. So we should not have the activation for the ring opening. And actually, this is a positively charged species. So this essentially should kill the ring opening, because you don't want to generate an allyl cation on a molecule that is already positively charged. So we were hoping we could use these as substrates, perform reductive elimination to generate these amines. Then we were hoping that this would open, and the literature told us that perhaps we could hope that the ring opening could proceed at room temperature. But we had no idea of the actual conditions and if we would need to heat eventually or not. And then we were hoping we would get these kinds of cyclic iminium species, and we would have to see if what we can do with them, if we can do something useful or it's too difficult. And to access these salts, we were, this is the inspiration of the example I showed you in the literature, that one. So we hoped we could start from these box species. So these are amides, and the nitrogen atom is conjugated with the carbonyl group, and we were hoping this would be stable enough too. Okay, so this is how the synthesis went. So we started from this kind of Boc-protected pyrrolidine or piperidinone. In this example here, so with a 5-membered ring or 6-membered ring, we just reduce the carbonyl group. So we get a kind of a hemiaminal, which is protected. And then we have to eliminate the hydroxyl group. And we can do this by in refluxing toluene with a small amount of an acid. And the yields are okay. They are not excellent, but they are quite useful. And then we are performing the cyclopropanation with dihalocarbene, so using either chloroform or bromoform. And we can make these molecules in generally quite good yields. And these are conditions that were introduced by Professor Monkosza in Poland. So using phase transfer agents like this ammonium salt. So this works really fine. We also wanted to make compounds having a substituent at the ring junction. So to this end, we can add methyl magnesium bromide onto the carbonyl group and then eliminate the hydroxyl group resulting from the addition reaction. And we get similar products as these with an additional substituent. In this case, the cyclopropanation reaction proceeds in a lower yield, but we can still get the expected products in useful amounts. Another way was to use, so this is a more direct way, but a bit more tricky. We are using a classic radical reaction called the Karach-Sosnovsky reaction. So we're using a peroxide and copper 1 catalyst, and we can go directly from here to here. The problem is that this product is also a substrate of the reaction, and it can react again under these conditions. And we have another CH activation reaction that produces this acetate. So to avoid this or to minimize this, we need to use the starting material in quite large amounts and stop the reaction before total conversion. So we stop it when we still have a lot of starting material, and then we can have a reasonable ratio of these two compounds in favor of the one we want. Then we perform the cyclopropanation reaction. Of course, this one does not react, and we can separate it after the reaction. And both of these can be cyclopropanated, so we get these two products, which are quite easy to separate. This one is more polar than this one. Make compounds having only one chlorine atom, so we can do a chlorine to lithium exchange with S-butyl lithium in the presence of themeda. This is tetramethyl ethylene diamine. So this is to break the butyl lithium aggregates and make it more reactive. At that low temperature, so we generate the organolithium compounds that we just hydrolyze. And we get a mixture of these two diastereoisomers, almost a 1-to-1 ratio. It's possible to separate them. It's not very easy, but we can separate them. It's also possible to remove all the chlorine atoms altogether using a sodium metal in a refluxing isopropanol. So we have to be careful with this reaction, but this proceeds, of course, by single electron transfer. And we can end up with this one. So we were interested in this one, but not for this topic. We have no living group on this one, so we cannot do on it what we want, but we can do other things. Okay, so the next step was the removal of the Bock group and the synthesis of these ammonium salts. In fact, we do not need to use TFA. We can do this under much cheaper conditions, just with a few of a concentrated HCl aqueous solution in ethyl acetate at room temperature, and we get stable solids, so these salts. So the reaction is quite fast. We just evaporate the solvent at the end, and we get these salts. So this can be recrystallized or used directly as such, and it's fine as well. So we could make all of these salts. We could make the salts from the monochloro compounds as well, so that's fine too. And also from this more substituted compound, we could make this salt. And then we were ready for the reductive amination reactions. And this works. So we use this particular hydride reagent, which is quite a classic one for reductive amination reactions. We can get this aminocyclopropane. It can be observed by NMR. But then we observe that at room temperature, it decomposes slowly. So it's stable over about half an hour, and then it decomposes. And the final product we get actually is this molecule. So it results from the trapping of the allyl cation or iminium that we envisioned with the hydride reagent, which we had used in excess amounts. And this is quite a nice reaction, quite general, and we can get all of these heterocyclic compounds directly from the corresponding salts and the corresponding aldehydes. So with the ketones, so here on this slide, there are only two examples. So here we use the cyclohexanone, and you see the yields are typically lower. Also, yields are better when we make, when the ring enlarged product is a 6-membered ring. With 7-membered rings, it's a bit more difficult to get good yields. We were also interested into stereochemical aspects of these reactions, and this had been already studied by Charles Dupuy in the 1960s, except there was no nitrogen substituent, and he had shown very nicely that you see on this starting material, you have some substituents that are on the same face of the cyclopropane as the leaving group, and he showed that these end up in the inner position of the allyl cation. So, for example, if you start from this compound, so the chlorine atom is at the back, the hydrogen atoms here at the ring junction are at the front, so there are these orange substituents, and the ring, the 6-membered ring itself, is the purple substituent that will go in the inner position of the allyl cation. So you will generate this allyl cation, which is then trapped with the sodium acetate to form this acetate. Whereas if you start from the other diastereoisomer, now the substituents that are on the same face of the cyclopropane as the chlorine atom as the ring are the ring junction hydrogen atoms. So they have to end up in the inner position of the allyl cation. So in principle, the allyl cation you should get by after ring opening is this one, but this is of course a very strange structure, and consequently the ring opening is not observed in this case. It's totally inhibited. So we wanted to see if it's the same thing for us. So we prepared this particular salt that I showed you before, and this behaves exactly as the other substrate. So there is ring opening and then reduction of the iminium with the hydride reagent, we get this compound. Whereas the other diastereoisomer does not react. So, well, it does react with benzaldehyde. There is the reductive amination reaction to form this aminocyclopropane, but this doesn't open up under the reaction conditions, and we can isolate this. This is perfectly stable. So it's just an illustration of this nice observation that had been done by Charles Dupuy a long time ago already. Okay, so from there, we wanted to go further and make something more useful from the iminium intermediate. And we thought if we have an internal nucleophile on the substrate, we could make an additional ring and get access to a nitrogen-containing bicyclic system. And of course, that would be much more interesting because you can find this in a number of biologically active compounds, natural products or not natural products. So our first idea was to try simply the same conditions with this particular aldehyde, which contains an indole system, which is a very good electron-rich heterocycle and a very good nucleophile. So we were anticipating we would generate this iminium ion, and then this could be trapped intramolecularly by the indole, either at this position or at this position, to form either this product or this product. And when we tried this, actually, we did not observe the products we wanted, and that's a bit of a pity because this looks like this compound, which was shown to be a nice inhibitor of this protein, which is a virulence factor of this bacteria, which is responsible for tuberculosis. And instead, the product we obtained was this product, which is follows exactly the same reactivity pattern as the others. So what it shows is that, in fact, this iminium is really quite reactive, and in the competition between the cyclization and the trapping with the hydride reagent, the trapping with the hydride reagent is winning. And we even tried to reduce the amount of hydride, but we could not control the reaction, and this remains the main product. So we had a problem there, and we had to move away from this chemistry of amines, and we decided to switch to amides. So we knew the ring opening would be more difficult with amides. So we would have to heat probably to generate the iminium. But a very big advantage is that under these conditions, there is no hydride. So in principle, no competition between the cyclization and another reaction. And we hope to make these compounds. So to make the amides, we thought we could start from the same ammonium salts, and we could regenerate secondary amine with a base. So of course, this is an amine, so it can open up at room temperature. So this is not stable, but reactions of amines with acyl chlorides are fast reactions, and we hoped we could trap this with an acyl chloride before it rings open to get the more stable amide. So again, the products eventually we wanted, well, we hoped we could make were at this structure. And perhaps it's even better than the amine to start with the amides, because this kind of moiety can be found in a number of interesting natural products or drug candidates like this one. Okay, so we tried the reactions. We started with a classic Schotten-Baumann type conditions for the reaction of the amine with an acylchloride, and that works reasonably well. So we have a biphasic system with a solution of sodium hydroxide and dichloromethane. So under these conditions, this is deprotonated, and then there is a fast trapping with the acylchloride to form this product. When we wanted to do the same thing with the similar salt having a methyl substituent here, in fact, the reaction becomes slower, and we had 0% yield of this. So it's because of the presence of this methyl group, so it slows down the trapping with the acylchloride. And then this has time to open up. So it goes to this iminium, and this is hydrolyzed under the reaction conditions. We have some water, and this liberates this primary amine, and this is the one that is trapped with the acylchloride, and the product we could isolate is this one, which is not at all what we wanted. So we had to develop other conditions to make the aminocyclopropane. And what we were hoping is that at a lower temperature, this ring opening from here to here would be slower, and this would give time to this molecule to be trapped by the acylchloride. And to this end, we developed other conditions. So at minus 78 degrees, we add triethylamine as the base. So this also liberates the amine, but we are at a very low temperature. At this very low temperature, there is no ring opening, and this can be trapped. And then we allow slowly the temperature to go back to 0, and then we do the workup, and we get this compound in good yield. So these are conditions B. The classic conditions are conditions A, and we could make all of these compounds either under conditions A or conditions B. In general, with moderate to excellent yields. So actually, in our previous work that we published in 2017, we had tried one ring opening reaction. So it was using this compound. So it was starting from a monochloro compound, and we could make this amide. And then we heated this under microwave conditions, like quite high temperature. We could open the cyclopropane, so we had the ring enlargement we wanted. The iminium we wanted was generated, but it turns out that this compound is a very acidic compound. So this loses a proton instead of cyclizing, and this is the compound we obtained. So that's rather interesting too, but not at all. It's still less interesting than what we wanted to do. So we wanted to have another go at it. So with dichloro compounds, and also when we know that when we have a 5-membered ring, it's easier to ring open the product. And again, there was no cyclization. We have a similar reaction outcome. So again, this is very acidic. It loses a proton quite readily to form this compound, which is because this is very acidic. This is a very weak base. It's difficult to reprotonate it. Okay, so still we worked a lot on that. We thought that maybe if we have OH groups instead of O-methyl, and then if we trap the dihydroxyl group with a boron compound, this would be more nucleophilic, and we would have a chance to cyclize it. And actually, that worked. So with a BF3, we can deprotect this acetal. And we have also a base. So in fact, we have a phenolate type nucleophile here. And under these conditions, we could manage to form this product directly. but unfortunately the yield was rather low, 30%. And unfortunately, this is our best result. So this was not very satisfactory. We had to think again, and we came up with this solution. So we performed the reaction in 2 steps in one pot. So first, we ring opened the cyclopropane to form this intermediate. And as I told you, this is a weak base. So from here, we have to regenerate the iminium. And because this is a weak base, we need a very strong acid. So we take a sulfonic acid and we have to heat again. And this gives us, at last, the expected compound in a reasonable, acceptable yield. When we have a 6-membered ring here, we found that it's more difficult to have the ring enlargement. So we have to heat more at so with a 1,2-dichlorobenzene, we are at 180 degrees instead of 80 or 90 degrees with acetonitrile, and still the reaction works. And then we try to make a different bicyclic system. So with a 5C6, it's quite difficult, and the reason is if you look at this carbon, it's an sp2 carbon. It wants to have an angle of 120 degrees. Same for this one and this one. So all of these want a 120 degrees angle, which is quite far from that in a 5-membered ring. So it's quite difficult. We can still make this one, 38% yield. This one almost doesn't work because when we start the substrate, so there is no bond here, so we can make the new bond here or here. So we have an ortho substituent that hinders the reaction, and this is why it doesn't work well. And this one has the methoxy substituent at the wrong position, so we do not benefit from the electronic effect of this group, and the reaction is more difficult. 6,6 fused membered rings. So here also it doesn't work for the same reason. Here the electronic effect is okay, but we have only one donating group. So the reaction works, but in a rather low yield. This is the example I showed you before. So this one works. We have an electron-rich ring, and one group has the right electron donating properties to activate this position. And here we have a more substituted compound. So this position here, sorry, I can see a comment by Asmi. Is it for me? Oh no, for participants. Okay. So here the reaction is slowed down by the presence of an ortho substituent, but we have 3 donating groups, so the reaction still works okay. 6-7 system, so this one works well because we have 2 donating groups, and this one has a methyl group at the ring junction, so it's more difficult. It still works, but in fact the problem is not the cyclization itself, it's the ring opening. We found it's very difficult in the case where we have the methyl group, and we even have to use silver salts to help removing one of the 2 chlorine atoms. And under these conditions, we can make this, but you see the yield is not fantastic. And then when we have a 7-membered ring that we are making here, also this is a difficult reaction. In general, making 7-membered rings is quite difficult, and the yield is only 18%. But the reaction is interesting, so I show you. So this is the product we isolate in 18% yield. But we also get this product, which is quite surprising. You see, it's like the same one, but with the double bond at a different position. And we also have this cyclized product where we lose totally the nitrogen part. So this is less interesting. And this is what we observed in the crude product after the purification. So I told you we get this one in 18% yield. We could not isolate this one. We could isolate this alcohol. So this results from an SN2 prime reaction of water coming as a nucleophile and substituting the chlorine atom. And so we have the proof of structure of this because we have the X-ray structure. And this one here, so I will tell you how it's formed. So to explain these results, in fact, when we look at this compound, it can be protonated at 2 positions. So either at this position, which is the least hindered position, and this generates the iminium we observe in general. So this is expected to be quite fast, but protonation at this carbon atom that bears the chlorine atom is also possible. This also gives an iminium. So this must be slower because you have a substituent here. So this slows down this. And then when we look at these 2 iminium species, this one is conjugated, so it's quite stabilized. So we expect that it will be also less reactive, which is not a problem in many cases. But when the cyclization is difficult, so making a 7-member ring is difficult, then perhaps this pathway can become predominant or at least competitive with a more reactive iminium, and we can start to observe this kind of product. And another possibility, which shows that these reactions are in fact quite complicated, is just protonation at the amide. So on the carbonyl, I think this is in fact the most favored pathway, and of course this is reversible. Otherwise, we would have a lot of problems. And then we can have direct cyclization at this carbon, in this case, to form eventually this product. So I'm almost finished. So another unexpected result was this one. So when we worked with this dibromo compound, we obtained the expected product, but this was not the major one. The major one was actually this very strange isomer, where not only the carbon-carbon double bond is at the other different position, but also the bromine atom is at a different position. And this is really very, very surprising. We analyzed again the intermediate, and we found that actually some isomerization had taken place already at during the first stage of the process. And it's possible to explain it, but it's quite complicated. So we think this results from protonation again at this position rather than at this position. So protonation here to form this iminium. This is quite an acidic species, so it can lose a proton to form this azomethanilide. And then if you push the arrows, you can eliminate the bromine to form this new iminium species, which is an electrophile, and the bromine atom can come back. So it could come back either here or at this position, and in which case you get this new azomethanilide. This can then get protonated to get this compound, and then this can eventually lose a proton to get this product, which is the precursor of the unexpected product. Okay, so I reached the end. This is the last chemical slide. So this is a kind of summary. So we showed that starting from amides of this type, we can generate this kind of iminium, and we can, under well-chosen conditions, perform cyclization to form these compounds. This is actually the cover of the Organic and Biomolecular Chemistry issue where our article was published this year. And this is a very nice drawing done by a Czech student from Palacký University. And she's a fine artist as well as a chemist. And we have a collaboration with this university. They knew this artist, and she agreed for free to design this cover for us, which I find personally is a very, very nice, very colorful, and very beautiful. Just to finish with a few words on Ecole Polytechnique. Perhaps some of you already saw this slide, so I will go very quickly. So our school was founded a long time ago in 1794 during the French Revolution. And Napoleon gave it a military status 10 years later in 1804. It is still a military school. This is why students have uniforms. They don't have to wear these uniforms every day, so only on special occasions, like the annual ball at Opéra Garnier in Paris. Unlike most universities, there is a selective entrance examination in our school, and students do not specialize until the final year. So it's quite a multidisciplinary school. Here it's actually the old logo. I forgot to change it, so it's written Université Paris-Saclay, but now Ecole Polytechnique is not part of Université Paris-Saclay anymore. So it actually they started a concurrent alliance, which is called the Institut Polytechnique de Paris, and it was created a few years ago. It's doing very well. So it's an alliance between 5 engineering schools, including Ecole Polytechnique. And the current QS ranking is 38th position in the world. This is what our campus looks like. So this is the teaching part of the schools where the amphitheaters are. This is the research center. These are accommodation for students. These are sports facilities. And this slide is just to show you that there are quite many famous former students from our school. In green, I highlighted the chemists. So Gay-Lussac is quite famous. Auguste Caour, Darzens. There is a Darzens reaction. And it remains me to thank the students and postdocs who worked on this project, this aminocyclopropane project. And the key player, the most important one, perhaps, is Veronica. So she came for internships 2 times 6 months in 2 different years. She's a Czech student, and she did all of the work with the cyclization that I showed you at the end. So I have to thank also the mass spectrometry guy, Vincent Jactel, and Lucy Brolikova, who is the PhD, who was the PhD supervisor of Veronica. Now Veronica has defended. And of course, I have to find all of the funding institutions. This is very important. So this is Institut Polytechnique de Paris. So this is the new logo. This one I didn't forget to change, but I forgot the other one. And thank you very much for your very kind attention, for the invitation once again. And sorry, I think I went a bit past schedule, but
it's okay.
It's okay.
It's good.
Thank you. Thank you very much.
Okay. Thank you very much, Dr. Yvan Six, for very nice presentations and sharing sessions regarding the organic synthesis. I hope everybody who attend these sessions can learn a lot. We hope one day our country have this kind of chemistry. So before we finish these sessions, I would like to open for questions. You can write down the question on the chat box, or you can have a face-to-face sessions to ask the questions. Okay, anybody have question? Maybe I can start a few questions regarding this topic today. The first one, regarding the aminocyclopropanes, we need an anhydrous condition to do reactions. Do you think Malaysia is good to do that?
Yeah, it's okay, I think. So I can go back. Well, it's difficult if you use the titanium chemistry, because you have to work with Grignard reagents, and I think it's not super sensitive. So if you can work under argon, you don't need a Schlenk line, for example. You know, if you can work with balloons filled with argon, even if the flask is a bit moist, it should be okay, I think. For these reactions, a bit of water is not very good, but maybe well, the yields will drop by a few percent maybe for the second step, because maybe you will not have that strong an acid. It will be it will be protonated water instead of the sulfonic acid.
Okay,
I think
it's
it
me.
should
We
still be
need.
okay. And for the synthesis of the precursor, it will be fine. Like you see here, anyway,
Okay.
we have water. So yeah.
Okay. Nice. Okay. The second question: have you tested for this final product with biological activities?
Yes. So in fact, Lucy Brolikova, our collaborator from the Czech Republic,
Okay.
is very interested in anti-tuberculosis activity, and she has collaboration with biologists in Belgium. So they wanted to test our products. So I mean, this kind of products, yeah, these cyclized products. So this family of products, but they couldn't find a very interesting activity. So
Okay.
after that, we gave these products to the National Chemical Library. So the compounds are available for biologists who are interested. So
Okay.
so far, I didn't get any feedback, but I think there will be some tests. Yes.
Okay. I have another two more questions. Do you
Okay.
face any do you face any problem during the separations? Or we need to do column chromatography or HPLC for this?
In general, we need to do column chromatography. Yes. Yeah. And some of these compounds are actually crystalline, so we could purify some by recrystallization.
Okay.
But if I remember well, it's not the general case. I saw there was a question, but it
Yes,
showed
there's
for
a
me
question
only
from
for
Prof.
a few seconds, so I didn't have time to read it, unfortunately.
Okay, maybe I can
Can
read
you
for
read
you.
it for me? Yeah.
Yeah. Have the azasteroid compounds have you synthesized show any activities?
Oh,
In
okay. So it's
earlier
a bit the same
presentation,
question.
you explained about the azasteroid.
The azasteroids. Yeah. Sorry. So it's not the same question. It's I have to show them again. Where are they? Here.
Yes.
Yeah. If so, this was done 10 years ago, so I can't
Yes.
remember very well. I think we gave them to the chemical library, but there may have been some activity, but nothing very remarkable, because I'm sure of that. I would remember, of course. Yeah.
Okay.
So maybe there was some moderate cytotoxicity or something like that, but very moderate and not very interesting, unfortunately.
Yeah, nice. I hope Dr. Yvan Six is answering your question, Prof. So I think this is my last questions. In slide 34, you explain about the unexpected result regarding the cyclization. How you deal with that? Because sometimes we come up with the
44.
34, 34,
34.
34,
54.
34.
34. Okay, so it's the one that is shown here.
Yes.
Yeah, well, it's not that unexpected. We knew there would be a competition between the cyclization and the reduction. So unfortunately, it's the reduction that wins. Yeah.
And how you change the idea from
So
from the earlier
the
proposed
problem is that, yeah, so to solve this, we need to have the reaction without hydride, right? Because we know if there is an hydride, it will trap our iminium. But the problem is that we need the hydride to make the amine. So the alternative perhaps would have been to make this kind of amine by an SN2 reaction, but this is much slower than a reductive amination or trapping with a acyl chloride. And I think we did try, but in this case, the ring opening takes place before we substitute the nitrogen. So this is how we moved. So we didn't want hydride, and making an amine was too difficult because the intermediates were not stable enough. So this is why we changed and decided to move to this chemistry with amides.
Okay.
We knew there was a price to pay, which would be more difficult ring opening. We knew we would have to wait, but that's okay. When we have a 5-member drink, 80 degrees is enough, so it's quite mild conditions. It's okay.
Okay, thank you very much. Anybody have questions before we close the sessions? 1, 2, and 3. Okay, I would like to say thank you again to Dr. Yvan Six for today's sessions. It's good for us to learn a lot about the organic synthesis, challengings, and also very interesting. So, and again, thank you, Dr. Yvan, for your time. And hopefully I can come and visit you next year, maybe, hopefully.
Yeah, I was very happy to share our results, and it was a very nice discussion after it. So it's very nice. Thank you very much again for the invitation.